Hi students, welcome back to the continuation session of first unit. Once again, we will discuss about the other topics remaining in your first unit. So in our previous session, we have discussed definition of data structures, and then we discussed about classification of data structures, followed by operations on data structures, and finally what is an abstract data type. So we covered all these topics in our first session, and today we'll focus on preliminaries of algorithms, and then how to calculate time and space complexities of algorithms. We'll consider some examples and how to represent these time and space complexities also, right? Now, what is an algorithm? We'll begin with the definition of algorithm. I think all of you learned this definition in your first year. So algorithm is simply a sequence of instructions which are used to solve a particular problem at hand. Or you can write it as a step-by-step method of solving a problem for solving certain problems. So you can use any of these two definitions. Simply, you need to remember that algorithm is specifying the solution to a problem in the form of steps, right? And while writing the algorithms, you need to remember their characteristics also. Every algorithm that you develop must possess all these properties or characteristics. I will go through one by one. The first characteristic that should be possessed by the algorithms is finiteness, which means every algorithm must always terminate after finite number of steps. That means there should be some stopping point for your algorithm when it is executed. Okay. Otherwise, if it is not terminating, then there will be no use of it. Somewhere the algorithm must stop its execution. And the second property is definiteness. Definiteness says that every instruction that we write in the algorithm should be clear and unambiguous. That means there should be no confusion while performing that particular instruction, because instructions are given to computer through our algorithms. Every instruction must be clear enough so that the computer should not be confused. To understand this, for example, say add 3 to 4 is an instruction which is very clear. It is saying that add 3 to 4. So computer can understand the instruction and adds 3 and 4, produces the corresponding result. And then if you consider another statement, add 3 to 4 or 5. What does it mean? Add 3 to 4 or 5. You're giving the option to the computer. That should not be a valid statement in your algorithm, right? So definiteness says that every instruction that you write in the algorithm should be clear and unambiguous to the computers. And the third property is about number of inputs that can be submitted to an algorithm. Algorithms expect 0 or more inputs. That means you may submit some inputs to the algorithm while running it. Otherwise, you may not submit any inputs also. You can directly ask the algorithm to run straight away without any input. Okay. And then the fourth one is output. Whenever we write an algorithm, the purpose is going to solve a particular problem at hand. And when you are solving a particular problem, it should always produce some output. At least one output is expected from your algorithm. Otherwise, there will be no meaning for the algorithm. Therefore, algorithm should always produce one or more outputs. At least one output should be produced. It may or may not take inputs, but should produce at least one output. And the fifth property is effectiveness. This effectiveness actually has two meanings. One meaning is every instruction in the algorithm must be basic enough so that a man can sit aside and he can perform that instruction manually, right? So whatever operation you mention in the algorithm, that should be basic enough so that anybody can do it manually with a piece of paper and pen. So that is one meaning of effectiveness. There is another meaning for effectiveness also, saying that every instruction in the algorithm should contribute towards the final output of the algorithm. So if you write irrelevant instructions in between, it's not going to be an algorithm. That means every statement or every instruction we write in the algorithm should be relevant to the algorithm only. Unnecessary statements or unnecessary instructions should not be written in the algorithm. So effectiveness has two meanings. One meaning says that the instruction must be basic enough to calculate it manually, and the other meaning is irrelevant instructions should be avoided, right? Uh, and in addition to these five properties, there is one more property that is expected to be followed by the algorithm designers, which is called as generality. Generality means that writing algorithms should not be using any existing programming languages. That means you cannot write an algorithm using C language, or you cannot write an algorithm using C++ language. It should be written in a general terminology. So maybe you heard about pseudocodes in your first year. Most of the cases, pseudocodes are preferred for writing algorithms. Okay, and have a look at this example. Uh, this is a simple algorithm which adds two numbers. Okay, step one is start. Step two is declare any two variables. Let us say num1 and num2, and another variable for storing the result. Step three is read the values num1 and num2, and step four is add those numbers and assign the result to sum. Okay, and finally display the sum, stop the algorithm. So this is a simple example. Maybe this is a very general way of writing your algorithm, but you can use pseudocodes for proper understanding of the algorithms, right? Now, what does algorithm complexity mean, and why we need to measure this algorithm complexity? Algorithm complexity is actually measured in two ways. One is in terms of time complexity, and the other one is in terms of space complexity. Time complexity is nothing but the CPU time required for executing a program, and space complexity is nothing but the amount of computer's memory required for executing your program. Okay, so time complexity is the amount of time required by the CPU for executing the program to its completion, and space complexity is the amount of computer's memory required for executing the program to its completion, right? So this is called as algorithm time complexity, and even before we convert our algorithm into a program, we need to analyze the algorithm properly. We need to identify what is its complexity in terms of time and space. Why we need to analyze this time and space complexity is the reason is very simple. Because for a particular problem P, there may be number of solutions, number of algorithms available, A1, A2, so on, AN. Among all these algorithms that are available for solving a particular problem, you can compare the performance of these algorithms in terms of this time complexity and space complexity. Whichever algorithm takes less time for execution, and whichever algorithm takes less space while execution, that algorithm will be considered as an efficient algorithm for solving that particular problem. So for comparing the efficiency of algorithms, you need to measure the complexity of the algorithm in terms of time and space. Okay. And now, how do you specify these time complexities? What is the measure of unit for specifying the time and space complexities? So there are special category of notations available for specifying the time complexity and space complexity, which are called as asymptotic notations. Asymptotic notations are basically used for representing the time complexity and space complexity. So you remember that single aspect of asymptotic notations, they are used for representing the time complexity and space complexity. Okay, why we require a special notation for representing time complexities? We need to understand that first. So let us understand it with an example. If you look at the first algorithm, this slide contains two algorithms. If you look at this first algorithm, uh, algorithm first, its name is first, and it takes two parameters, two input parameters, and then the body of the algorithm contains a single statement which is calculating addition of the given two numbers and storing the result into another variable res. So how many statements are there in this algorithm? Only one statement is there in the algorithm. Therefore, in earlier days, in the uh, earlier representation of time complexities, people used to represent the time complexity in terms of number of statements executed in a particular algorithm. So the time complexity is 1 for this algorithm. That means this algorithm requires 1 unit of CPU time. Okay, and then look at this second algorithm. Again, name of the algorithm is second, and it also takes two parameters, a comma b, and it is calculating the result as a into a plus b into b plus a by b plus a into b plus a minus b by a. Even though this statement contains a number of sub-operations, people use it to measure this as a single unit of operation. Therefore, the time complexity of this algorithm is also 1 unit of time. Now, is that correct? To represent the time complexity of this algorithm as 1 unit of time exactly, and to represent the time complexity of this algorithm as 1 unit of time exactly? No, that's not correct. So therefore, because even though algorithm contains single statement only, their time complexities are different. So whenever we talk about time complexities, we should not mention exact measures. There should be some approximation measure available for representing the time complexities, because this requires very less CPU time for execution, whereas this requires very uh, high time compared to this, because it involves number of basic operations, a into a, b into b, a by b, a into b, a minus b, b by a, and then adding all these sub operations. Therefore, you should not say this requires 1 unit of time and this requires 1 unit of time. There should be a proper way of representing time complexities, which should be an approximation of existing time. Okay, so that is what these asymptotic notations provide. Now, if you look at the types of asymptotic notations, they are classified into 5 categories. Among these 5, only 3 are popularly used. Remaining 2 are not actually used that way. But we will discuss about all these 5 notations now. The first one is big O notation, and the second one is big omega notation. Third one is theta notation. People call it as big theta notation also. And a variation of big O notation is little o notation, and a variation of big omega notation is little omega notation. So let us have a look at all these notations and how the time complexities are represented using these notations. So it's not easy to understand asymptotic notations because it involves some maths over here. You require some function concepts. Should have some basic function concepts. You should know them, because all these notations involves functions. Okay, so let us understand the definition first. Assume that f of n is the uh, time complexity identified through the traditional methods. Let us say some 2n square plus 3n, something like that, an exact measure. And because we identified that exact measures are not correct to represent the time complexities, we are trying to represent it in the form of asymptotic notation. Okay, so for that purpose, what we do is we consider another function g of n. Okay, I want to represent f of n using asymptotic notation big O. Therefore, I look for another function g of n in such a way that f of n can be written as less than or equal to some constant c into g of n. You must be able to write this for a given f of n and g of n combination. Then you can write it as, if you are able to represent f of n and g of n like this, then f of n can be represented as big O of g of n. Okay, and how do you pick this c? Depends on the corresponding example. Okay, and for it is possible that for every n value this may not be satisfied. So therefore we look for the range of values where this equation is going to be satisfied. So we assume that starting from k, k plus 1, k plus 2 and so on, this equation is going to be satisfied. Okay, right. If you look at the diagram, f of n is here and c into g of n is here. F of n is always less than or equal to c into g of n. You need to identify a value k. It is wrongly written over here. It is not correct. I request all the students to note down this k over here, because from here onwards, if you look at f of n and c into g of n, f of n is always less than c into g of n. That's what we expect. Okay. From this value, from any k value which is over here, before this value there may be some fluctuations. F of n may be bigger than c into g of n, c into g of n may be bigger than f of n. It's not stable over here, but from here onwards, from this value onwards, f of n and c into g of n are always steadily related. F of n is always less than or equal to c into g of n. So please keep this k over here, right? So this is about the asymptotic notation big O. Simply saying, there are two functions. F of n is the time complexity and g of n is the function which we are considering. If you can represent f of n as less than or equal to c into g of n, where c is any constant, then you can write f of n as big O of g of n, right? Have a look at this example, you will understand it now. Suppose the function is f of n is equal to n square plus 1. This is the function, and this n square plus 1 now need to be represented as big O notation. So what I need to do is, I will consider that f of n, that is n square plus 1, and I will try to represent this as less than or equal to 2 into some value or any constant into some function. This g of n is also your choice. Constant is also your choice. So when there is n square plus 1, if I pick 2n square over here, assuming values of n as greater than or equal to 1, this equation is always going to be satisfied, right? You can check it. So for c is equal to 2 and k is equal to 1, this equation is satisfied. Therefore, what I can represent is, I can represent this f of n as big O of n square, because I'm able to write it as less than or equal to 2 into n square. Ignore the constant, and this is g of n. Okay. Therefore, I'm representing that equation n square plus 1 as big O of n square. Okay. Now you may get a doubt over here. Instead of considering n square, can I consider n cube? Yes. If it is less than or equal to 2n square, this is definitely going to be less than or equal to 2n cube also. Definitely going to be less than or equal to 2n power 4 also, and so on. So you can consider any value. All of them beyond this n square are going to be upper bounds for this n square plus 1 only. But the thing is, among all those upper bounds, you need to pick the tight upper bound only. So for n square plus 1, the tight upper bound is n square. N cube is an upper bound for this n square. N power 4 is an upper bound for this n square, and so on. But the nearest upper bound, which is also called as tight upper bound, you need to consider. Therefore, we take this 2n square only. Or in place of this constant, you can pick any value, not only 2. C can be any value, so that this is going to be satisfied. Okay. I think I'm clear with this. You can consider any upper bound, but you need to choose the tight upper bound only. And there is another example given over here, n power 4 plus 100 n square plus 50. Again, I'm using 2 n power 4 here for n greater than or equal to 11. For n less than 11, maybe this equation is not satisfied. Therefore, you need to identify for what values it is going to be satisfied. Okay. Therefore, this equation can be represented as big O of n power 4. Right. The second notation is big omega notation. Big omega notation is actually opposite to omega or big O notation. Big O notation represents upper bounds and big omega notation represents lower bounds. That means f of n is always greater than or equal to c into g of n. So whatever function you select, it must be smaller compared to f of n. Therefore, we say that big omega notation is a lower bound notation. Okay, so if f of n is represented as greater than or equal to c into g of n, then you can write it as f of n is equal to omega of g of n. So please remember this notation, omega is represented like this, right? And you can see it here. Again, in this diagram also, k is wrongly written over here. Please draw it over here. From this position onwards, f of n is always greater than c into g of n. You need to identify that c into g of n in such a way that f of n is always greater than. Okay. And again, the same two examples are written over here. This time, I took this n square plus 1 greater than or equal to n square. I'm not using any constant, which means 1 into n square. Okay, so n square plus 1 is always going to be greater than or equal to n square only, right? Therefore, I can write it as omega of n square. Now you can get a doubt over here. N square plus 1 is always greater than or equal to n. Yes, it is correct. But you need to pick the tight lower bound again. Greater than or equal to n is correct. Greater than or equal to 1 is correct. But you need to pick the tight lower bound, the nearest lower bound, right? Therefore, omega of n square is correct answer. Similarly, for this also, n power 4 plus 100 n square plus 50 greater than or equal to n power 4 I am writing. Okay. Therefore, this can be represented as omega of n4. Right. And the third one, theta notation, is a tight bound, not upper bound, not lower bound. If you look at the diagram, this is, you need to identify two constants, C1 and C2, such that represent this f of n as c1 into g of n less than or equal to f of n and less than or equal to c2 into g of n. So c1 into g of n less than or equal to f of n less than or equal to c2 into g of n. So f of n should be a value between c1 into g of n and c2 into g of n. Remember, it is g of n, same g of n only. You cannot use one g of n over here, n square over here, another g of n, n cube over here. You cannot use like that. The same g of n must be used with two different constants in such a way that f of n falls between these two. Okay, then you can represent it as theta of g of n. So f of n is equal to theta of g of n. I'm giving this example for you. I hope you can solve it. What you need to remember is 2n cube minus 7n plus 1 must be represented with c1 into g of n less than or equal to 2n cube minus 7n plus 1 less than or equal to c2 into g of n. Identify that g of n, because g of n is, answer is given over here. So you assume that g of n is n cube only. So you need to identify what is c1 and what is c2. Okay. So that's it for this session. Again, I'll just briefly go through the things which we covered. What we covered today is, we defined what is an algorithm. Algorithm is simply a step-by-step process of solving a problem, and the properties of algorithms: finiteness, definiteness, input, output, effectiveness, and generality, followed by how to measure the time complexity and space complexity, the notations used for representing the time complexity and space complexity. There are 5 notations: big O, theta, big omega, little o, and little omega notation. Coming to little o and little omega notation, they are same as big O and big omega, except that the condition is f of n less than or equal to c into g of n is replaced by f of n less than c into g of n for little o notation. For little omega notation, it is f of n greater than c into g of n. That is, equality is removed. Everything else is same. Okay. Thank you. We'll see you again in the next session.